A minute. Okay. So in the last class, we started with 2D geometrical transformation. So in 2D geometrical transformation, we have three things. One was the translation. So translation means there will be a point somewhere and you're moving that point to a new location. There is a point called P at some location X comma Y. You're moving that point to some other location. So in this new location can be X dash, Y dash. So that we will call it as the translation. The translation for that the equation is given by X dash is equal to X plus Tx, Y dash is equal to Y plus Ty. Yesterday I derived all these things. Simply I'm just put it in a slide. X dash is equal to Tx, Y dash is equal to Y plus Ty. Means you're getting the new position of X dash and Y dash by adding a shift vector value. Tx is along x-axis and ty is along y-axis. Meaning this is for x coordinate, this is for y coordinate. So the same thing, you can represent it in matrix form also. So this x and y, a point x and y can be represented in a coordinate system. Um, the x and y in coordinate system can be represented in the matrix form as a single column matrix. So P is taking x comma y is equal to x dash y dash plus t. So you can generate P dash. P dash is equal to P plus t. Nothing but the same equation which is being written in the matrix form where P is taking xy, T is taking tx, ty. So this is regarding the translation. The same thing. Uh, the next transformation which we studied was rotation. So rotation means rotating an object. So there will be an object. Here there will be an object. So I want to rotate this object about some point. So if I want to rotate it around 45 degree, so this 45 degree I can take it as theta. So rotating an object. So positive means anti-clockwise direction, negative value means clockwise direction. So for this also we got some equations where the x dash is equal to x cos theta minus y sin theta and y dash is equal to x sin theta plus y cos theta. And this equation can be represented in terms of matrix given by P dash is equal to R into P, where R is given by the matrix value cos theta minus sin theta, cos theta. So this is for the rotation. The same way, rotation means rotating an object from a specific point. So this calculation is done keeping in mind we are rotating an object with respect to the origin. The scaling means increasing the size of the object. For the coordinates x, we are multiplying with some scaling value. For this y, we are multiplying with some scaling value. If both these values are same, if both this s x and sy are same, as x is not equal to sy, we'll call it as differential scaling. So some of the things which we had studied in yesterday's class. So after this, all these three equations can be represented in a single form. P dash is equal to m1 into p plus m2, where m2 will act as m2 contains a single column vector which will take care of translation. So when the translation is to be performed, it will contain the tx and ty value, and this m will contain the identity matrix. It will contain the identity matrix, which is in 2 cross 2 format. 2 cross 2 format. But when it comes to the rotation and scaling, so this m1, it will contain what this m1 will contain means the values that are needed for rotation and scaling. So when it comes to scaling and rotation, this m1 matrix will contain the values that are needed for, see, when it is rotation means the value needed for the transactional values needed for rotation, and when it is scaling means the values needed for I mean what do we call that, that the terms which are needed for rotating. So m2 for rotation and scaling, m2 will contain the terms associated with um, with the scaling or rotation about a fixed point or about some pivot point. So for rotation it will be pivot point, and for scaling it will be fixed point. See the that is regarding for the rotation and scaling. So for rotation and scaling, um, this is how. So um, this is how it has been done. So we can check that m1 is a multiplicative factor. M1 is a multiplicative factor, and m2 is a additive factor. So m1 contains a 2 cross 2 matrix. M1 contains a 2 cross 2 matrix. Um, yeah, that's all. So this is regarding the equation. So after this, since here it contained like two things. One, like it contained this equation contained multiplicative factor plus additive factor, like some operations. See, all the it contained three operations like translation, rotation, and scaling. But there was some additive factor, there was some multiplicative factor. So multiplicative terms, translational terms, so all these things needed to be combined to a single matrix. So for this they came up with homogeneous coordinates, where instead of representing all the transformations into separate matrix, they came up with the representation of all the three transformations in a single matrix of size 3 cross 3, where x comma y was represented in terms of xy, xh, yh, comma h, where the value of h when taken 1, where x was defined as x is equal to xh by h. When h is equal to 1, x used to become xh. So in this equation, you also know that xh is nothing but h into x. So 1 into x will become x, and 1 into x into 1 will become x, y into 1 will become y, and h we are given y. So the equation got transformed to x comma y comma 1. So and the third column and the last column took the translation values, that is tx, ty, and this the diagonal
Sir, PPT is not visible, sir.
pipet is not visible. Huh? One second, I'll just check. Now
Yes, sir, it is visible.
you're able to see this now, right? One second, I'll just change the slides also. Just check whether you're able to see that also. Now, is the slides visible now? Two-dimensional geometric transformation, where you will be talking,
Yes.
where you will be checking the subtopic as two-dimensional scaling. Is this topic visible?
Yes, sir.
Okay. So if in between, if the slide is not visible, you just let me know, um, so that I can check what is the reason. So okay, again I'll start with this slide since it was not visible. Um, See all this translation, rotation, and scaling can be expressed in the single equation. P dash is equal to P dash is equal to M1 into P plus M2, where M1 is a 2 cross 2 array. It will contain multiplicative factor. M1 will contain multiplicative factor. So M2 is a column vector. It's a single column vector which contains two rows. It will contain two rows. So it is for translation. It is for translation, or which in turn additive factor. It's an additive factor. So whenever you are performing the translation operation, whenever the translation operation is being performed, so M1 will become the identity matrix. M1 will be the identity matrix, and M2 will contain the translation values, that is the translation vectors Tx and Ty. So that is how it is being done. Or this is for translation. So when the operation like rotation or operation like scaling is being performed, m2 will contain m2 will contain the terms associated with pivot point when it is talking about rotation, or when it is about scaling means the fixed point when we are talking about scaling. So this m2, or when we are talking about rotation, it will contain the values related to pivot point. When the operation is being performed as scaling, it will contain the values related to fixed point. And so this equation can be converted. So here it is performing two separate operations, like one is multiplicative and additive. So this operation can be merged into a single equation. So if you are representing the above equation in terms of homogeneous coordinate, what is homogeneous coordinate means? You are representing x comma y with respect to three element representation, xh, yh, h. So x is defined by x is equal to xh by h. So for this h, if you are substituting, if you're taking the value of h as 1, so x will become xh, because we know that is by the equation. And also y will become yh, and also you know that xh is equal to h into x. So 1 means the same value. So this equation will be converted to x comma y comma 1. So now the same equation, the 2 point representation, can be converted into 3 cross 3 matrix, where the third column will contain the translation values tx ty. So the diagonal will take the values 1, the diagonal will take the values 1, and the third column contains translation values tx, ty, and the rest of the terms, and the rest of the terms depends on the equation which you will be deriving. So when it is translation means the third column will take the translation terms. When it is rotation means um, this will take uh, the angle, the cos theta sin theta values. And when it is scaling means this will take the scaling value. So this is how it will be represented. So now instead of representing that in the three instead of representing in two separate equations, now the same equation, all the three transformation can be um, explained, or it can be represented in a single matrix itself. So for that, is this slide visible? Two-dimensional translation matrix. Is this slide visible?
Yes, sir.
Yes, sir.
Okay. Now see, now the third column, instead of writing that p dash is equal to, what was that, p dash is equal to matrix 1 into p plus m2. So that is being represented in a single matrix itself. This single matrix can perform translation, rotation, scaling. So when it is translation, when you are performing a two-dimensional translation means, when you are performing a two-dimensional translation, the third column can take the tx and ty values. So for an identity matrix, you are just applying that third column with the translation values or the shift values tx and ty. So this is the matrix for two-dimensional translation. So p dash is equal to the translation vector into p. So what is this uh, t of uh, tx comma ty means? It's a 3 cross 3 matrix which is given in this form, so if you're performing the rotation means, you can check um, for the rotation, the angle is specified with cos theta minus sin theta, cos theta. So we have derived an equation yesterday. R is given by cos theta minus sin theta, cos theta. Yesterday we have derived this. If you remember, p dash is equal to R into p. P dash is equal to p plus t. So three equations. This is for translation, rotation, and another one for like p dash is equal to s into p. This is for scaling. So now Here, the same thing, these four terms will represent the rotation factor, the rotation factor. So this can be generalized. P dash is equal to R into P, the same thing. For the scaling, so you, for the diagonal, you are adding the scaling vector, the scaling along X term, scaling along Y term. So if you expand this, if you write this, we know that X dash is equal to Sx into X. So I will just multiply this. I'll just multiply this. So you'll get that. So first term, Sx into X, 0 into Y will be 0, plus 0 into 1 will be 0. So this will become 0, 0. So the output will be this one. So X dash is equal to Sx into X. The same way you can write it as Y dash also. Y dash will get it as Sy into Y. So this is the same thing which is represented in matrix form. So now we studied about all these three things, and also we found the inverse. So inverse means, see, there is a point P. You are moving in this direction to a point called P dash. If you want to move this in reverse direction, if you want to move it in the opposite direction, you'll be using the minus value or the negation value. So for the translation, if you want to find the inverse means, you just replace Tx with minus Tx, Ty with minus Ty. So you'll get the inverse value. And for rotation, I told you that theta means anti-clockwise direction, minus theta means clockwise direction. So for if you want to get the inverse of rotation means, just apply this theta with minus theta. So this is the final derived answer. This is the final derived answer. Um, Cos of minus theta will be cos theta. See, rotation we have got it as rotation. We have got the formulas cos theta minus sin theta, cos theta. I've replaced everything with minus theta. Cos of minus theta will be cos theta only. Sin of minus theta will become minus sin theta. Minus into minus will become plus sin theta. Again, the sign of um, this is sine of theta, no? So this will be minus, this will be okay. After this, again sine of minus theta, minus sine of minus theta means minus sine theta. Again cos of minus theta will become cos theta. So that is how the final R inverse for this R matrix have replaced theta with minus theta. So you'll get the final equation R inverse. So R inverse is nothing but the transpose of R. So if you interchange the rows with columns, you will get the transpose of the matrix. And for the scaling, the inverse transform is obtained by instead of Sx, replace that Sx with 1 by Sx. If instead of replacing y, Sy, replace that Sy with uh, 1 by Sy. So that is how you'll get the inverse for scaling. So till now, we have studied these topics. Yesterday, we have derived the equations for all these things. So now we'll be talking about transformation matrix. What is this transformation matrix? The two-dimensional composite transformation matrix. So now we have first thing is we derived the basic equation. After that, we are converted into 3 into 3 matrix. Now we will be, after that we found out the inverse transformation means multiple, composite means multiple. So when the equation involves multiple operations, so this m2 can be translation 1, this m2 can be translation 2. So when, for example, there is a point called P. I want to transform this point from, this is the initial point x comma y. From this point I want to translate to some other, I want to move this to some other point, x dash comma y dash. Again, from this point, I want to move it to some point called x double dash comma y double dash. So instead of performing instead of performing two separate translation operation, that is moving operation from this point to this point, again from this point to this point, so I can multiply these terms, I can multiply this matrix, because you know that t1, see t1 will be represented, so this x dash y dash can be represented as t1, and this um, x double dash and t double dash can be represented as t2. So instead of applying individual transformation on this initial point, you can combine, you can multiply this matrices You can multiply this transformation matrix, and then you can apply the operation on the initial point. Are you getting this? Did you understand? Yes or no? See, M1 and M2 are two separate operations. M2 is also translation. M1 is also translation. So instead of performing two separate translations, what you will do means you will multiply those translations. You'll find the product of those translation, and that translation will be applied on the initial point. So instead of applying the translation on this initial point to get an intermediate um, coordinate, and again for this again applying the translation to get the final point. So instead of doing two separate translations on an initial point, what you will do means you'll first find the product. You'll first multiply this translation, and then you'll apply the result on the initial point to get the final translation. So that is what composite means, multiple. So um, forming the product of transformation matrices. So here M1 and M2 are the two. This is one transformation, this is one transformation. So what I am doing means I am finding the product. I am finding the product of this transformation. I am finding the product of this transformation. So this is known as composition of matrices. So forming the product of transformation matrix, it is often referred as the concatenation or composition. So if you want to apply two transformations like T1 and T2 to a initial point called P, then instead of doing the transformation separately, you can find the product. You can find the product of those transformation, and then you can apply that to the initial point. So for translation, now we will talk with respect to translation. So for example, there is a point P. For that, I want to apply one translation called T1x, T2x. So on applying this translation, T1x, T1y, this point will move to some location called P1. Again, for this point, I want to apply the translation T2x, T2y to move to the final location P2. So instead of applying like this, what I will do means I'll find the product of this intermediate matrices. So you know that you know that you know that this t of tx comma ty. So in the previous equation you would have seen that. Hmm. So what is t of tx comma ty means diagonal matrix. Substitute the third column with the shift value. So this T2, I can write it as diagonal matrix. No, 1, 1, 1, 0, 0, 0, 0. Here T2x, T2y. After that T1, T1x, T1x, T1y. So this also 1, 0, 0, 0, 1, 0, T1x, T1y, 1. So now I should multiply this. Instead of applying the transformation separately, I need to find the product of this. 1 into 1, 1, plus 0 into 0, 0, 2 to x into 0, 0. It will be 1 plus 0 first column. So this is 0. Anything multiplied will be 0 only. The second term, 1 into 0, 0, 0 into 0, 0, plus 2tx into 0. So that's why you'll get the 0 matrix multiplication. 1 into t1x, 0 into t1y will be 0, plus t2x into 1 will be t2x. After that 0 into 0, 1 into 0, 2ty into 0. So I'll get it as 0. 1 into 0, sorry, 0 into 0, 1 into 0, 2ty into 0. Again, I'll get it as somewhere I think I'm making a mistake. 0 into 0, 1 into 1, 0 plus 1 plus 0. 0 into 0, 1 into t1y. So t1y plus t2y into 1. So you'll get it as t2y. So 0 into 0, 0 into 0, 1 into 0. Again, I'll get 0. 0 into 0, 0 into 1 also 0, 1 into 0 also 0. Again, 1 in 0 into 0, 0 into 0, 1 into 1. I'll get it as 1. So the final matrix, see, this is what I've got. This is a final matrix. So 1 0 1 0 t1x plus t2x 0 1 t1y plus t2y 0 0 1. So whenever two matrices are there, m2 and matrices are there, so m1 m2 is also for translation and m1 is also for translation. So at that point, what you can do means you can find the final product, which is the addition of individual terms. For example, for example, there is an x is at the initial point x comma y. So I want to move this with values 2 comma 2 comma 3. Again, I want to move this value with 5 comma 6. So instead of that, for this x itself, you can add these terms 2 plus 5. 2 plus 5 will be 7. 3 plus 6 will be 9. So instead of doing two separate operations for the initial point of x, comma y, add plus 7 plus 9 like that. So that is what it is represented in this matrix. That is what it is represented in matrix. Whenever you want to perform two scaling operations, you just add their terms, x term, y term. So that is what. So the matrix was represented initially like this. So now you are adding this values, means when you multiply, you will get the additive result. So t1 of x plus t2 of y, t1 of y plus t2 of y. So you can see that when two transformations are there, for example, from 2 comma 3, one transformation move the points from 2 comma 3, and the other transformation add some value offset like 5 comma 6. The final output will be 2 plus 5 7, 6 plus 3 will be 9. So this is how the two dimensional composite matrix is done for translation. So for translation also, the individual shift vectors are additive. So for rotation also the same thing. For rotation also, when you want to rotate and when you want to rotate an object first by theta 1 and then again by theta 2, instead of performing the two separate rotations, you just add that rotation theta 1 and theta 2. I mean, first you want to rotate an object by 45 degree. After that, you want to rotate the same object by 30 degree. Instead of rotating first time with 45 and next time with 30, you just rotate it by 75 degree. So that is what. So this is also common. This rotation is also what do you call this? Rotation is also additive. So this rotation is also additive. So if I want to show this demo means, if I want to show this how to prove this means, first you should consider what is r theta 2. What is r theta 2? So what is r theta 2? R theta 2 is cos sine cos. So first write that r theta 2, no, cos theta sine theta 0 0 1, again 0 0 1, the same thing, cos theta sine theta 0 0 1 0 0 1. Again you just check for the sign, uh, cos theta sine theta minus sine theta cos theta. So minus sine theta cos theta minus sine theta cos theta. So this is theta r of theta. So now r of theta 1 means wherever theta is there, theta 1 theta 1 theta 1 theta 1, and theta 2 means so first you have to write theta 2, no. So theta 2 2 2 1 1 1 1. So if you multiply the matrix, if you multiply this two matrix, you'll get the answer, which is the addition of those two angles. So you can try this out. So cos theta 2 cos theta 1, the first equation will be cos theta 2 cos theta 1 plus, so cos theta 2 cos theta 1 plus sin theta 2 sin theta 1. So first equation will be minus sin theta 2 sin theta 1. theta 1, and the last term will be 0. 0 into 0 will become 0. Again, the same way, cos theta 2 sin theta 1 plus sin theta 2 cos theta 1 plus 0. See, this is just the matrix multiplication. So if you multiply this, you'll get the rotation will be the addition. The rotational term will be addition. You can just try this out. See, I'm just given the matrix terms. You just find the multiplication of this matrix. If you're not getting that, means I will solve it in the another class. So the matrix multiplication is also additive. So if you take an example of scaling also, if you want to perform two successive scaling, means instead of doing it separately, you just get the result of that, which is nothing but the product of those two scaling. So these two equations, this is individual scaling s2, and this is in individual scaling s1. So these two can be combined. So x terms of s2 and s1 can be combined, and y terms of s2 and s1 can be combined. So this is also matrix multiplication. S2 into s1 plus 0 into 0, 0 into 0. After that, s2 into 0, 0 into 0, 0 into 0. So it is matrix multiplication only. If you multiply this m2 and m1, you will get the final matrix. So matrix composition means when successive operations are there. When successive operations are there, and then the operations are similar, you don't perform the operation individually. Just multiply the matrices, you'll get the final result. No, that final result you applied for the initial point. For scaling also, it is additive. So here what I just wanted to tell is, when the operation is multiple, you just multiply and get the result first, and for the result you apply the transformation with the initial point. So this is regarding um, the two-dimensional uh, scaling. So for rotation also, you can verify that the rotation is also additive. Additive means you are adding the angles. And for scaling, also, you know that you need to multiply those two scaling factors. So after this, you are rotating. It is like how you can do the rotation at a specific point. So you want to know, in this example, you want to rotate this triangle about this point called XR YR. So for that, what operations you have to do? So you know that you have studied the rotation with respect to origin. You have studied with respect to the origin. So in order to rotate this object, the first thing is, the first point will be move that object to the origin. So this is done by inverse translation. So that is minus xr minus yr. If you see, instead of moving it in the forward direction, the translation, if you apply inverse, means you will move it in the opposite direction. Instead of moving this point along this line, you are moving this point to the origin. So for that, perform inverse translation. That is the first step. Once you perform the inverse translation, you will reach the origin. It will come to the origin. So once it is moved to the origin, the second point will be rotation. So it is moved in the anti-clockwise direction, the theta will be positive. This is the second step. Move to the origin by performing inverse translation, then rotate the object. rotate the object. After that, after that, after the rotation is done, perform translation. Why translation? Means again you want to move that to the initial position. So first I brought it to the origin, I performed rotation, then once the result I got, I'm moving this back to the same position, xr comma yr. So this is the sequence of steps that is involved in rotation. Move to the origin by inverse translation, perform the rotation, then again do the translation. So this is the sequence of operation that is being involved. Um, so I can take it as T. One is the inverse translation. After that, inverse translation should be multiplied with the rotation, then again the translation. So these are the operations involved: inverse translation, rotation, inverse translation, rotation, again translation. So that is being represented here. So this corresponds to inverse translation, this corresponds to rotation. So this is t of minus xr comma yr. So this is rotation of theta, and this is t of xr comma yr. So that is what. So first perform the inverse translation. Inverse translation is given by this factor. You have studied, no? 111,000,000 tx. Tx is minus yr and ty is minus yr. So Tx is minus xr and Ty is minus yr. So that is being represented. And for this theta, cos theta, the R factor in three dimension representation. Again the translation. So again you are moving it back to that. So you find the product of this. You find the multiplication of these three matrix. First you multiply this and this. You will get 1 and multiply 1 and 2. You will get the result. And that result, you multiply that result with matrix 3. So you will get this as the output. So you will get this as the output. So this is the final equation. Final equation. The final equation is cos theta sin theta cos theta, and you will get this is the movement along the pivot position. So this also we have derived. Yesterday we have derived, no, x is equal to some xr plus some equation. So that is what. So you can check that also. So this is rotation along a pivot point. So the same thing you can, again the same thing goes with scaling also. So you want to scale along a fixed point. The first step will be do the inverse translation. Do the inverse translation. Get it to the origin. From the origin perform scaling. The scaling is done. Once the scaling is done, do the translation, meaning move to the same point. So sequence of operation is inverse translation, then scaling, then translation. So you can check that: inverse translation, scaling, and uh, translation. So this terminologies are self-explainable. See, this is s of s x comma sy. This is t of x f comma yf. This is the inverse where you are replacing with t with the positive values with the minus sign. So this is regarding rotating, like rotating an object about a fixed point, about the fixed point. So this will be the final result. So if you want to know the verify the final result, you should perform multiplication of 1 and 2 first. You will get some result 3. You'll get some result. So that result you multiply with matrix 3. You will get this final value. You can verify that I've performed the multiplication of this matrix and I've got the output. So you just try it out. Once all the concepts are done, if you have time, we will solve this multiplication also, or else I'll just take the image of whatever matrices I've solved and I will display it on the slide. So now this is regarding rotation about a pivot point and rotation about the fixed point. Now the next topic is the matrix properties. See, multiplication of matrix is associative. So see, m3 into m2, and after multiplying this result with m1 will be same as multiplying the last two terms with m3. So multiplication of matrix is associative. So that is like a into b, and then multiplying the result with c is same as multiplying b into c and then multiplying with a. But multiplicative is not multiplication of matrix is not same, like a into b is not same as b into a. Only when only when the operations, only when the same operations are present, like when translation is present, it will work. A into b will be same as b into a. When rotation is there, so a into b will be same as b into a. When scaling is there, a into b will be same as b into a. But when two different operations are there, translation followed by rotation followed by scaling, or scaling followed by translation, when the operations are different, the matrix will not be commutative. So that is an example. See here, first I'm performing here. See the example. First here I'm performing initially this is my object. I'm performing the translation. After that I'm performing the rotation by 45 degree. So this is the final position. This is the final position. But for the same thing, first I'm performing the rotation. After that I'm performing the scaling. I mean not the scaling, the translation. I'm performing the translation. See the result here. Here the final position is at some point, and here the final position is at some point. So keep this property in mind. Um, when the operation is same, when the operation is same, um, when the operation is same, it doesn't matter. But when the operation is different, the output depends on the order in which the matrix is being evaluated. So that is what in our first example, first I perform the translation and then I perform the rotation. The answer is different. In the second example, I perform the rotation, then translation. The answer is different. So these 2 points you just keep in mind. So after this, these are some of the basic transformations. In addition to this basic transformations, we have some more transformations called reflection and shear. So what is reflection? So reflection means it's like it's like a mirror. It's like a mirror. So a transformation which will um, produce a mirror image of an object. For an object, you'll get a mirror image that we will call it as reflection. So this reflection can be along x-axis, this reflection can be along y-axis also. So reflection means you will be rotating the image by 180 degree. The image will be generated by rotating it through 180 degree through the reflection axis. So here it can be either it can be the reflection can be along x-axis or y-axis. So in this line y will be 0, and for this line x will be 0. Any point on that line will be x will be 0. So the transformation which will produce a mirror image of an object, we will call it as the reflection. The image will be generated by rotating the object around 180 degree about the reflection axis. So when y is 0 means see here y will be 0. So we will call this as x-axis. When y is 0 means that is nothing but we are referring to the x-axis. So if you want to do the reflection, if you want to do the reflection about the line y is equal to 0 means, so here you just substitute. So you know that x, y, z, no. So you just substitute this y with -1. So what happens means if it was the original position of the image means here y is positive. So y is equal to 1 means it will be here, no. So if you supply this value with the negative term, so you will get the reflected position here y will be minus. So reflection about the line y is equal to 0 will be obtained by using this transformation matrix where the y value will be -1. So y positive, y negative. So the x value will remain. So what happens means the x value will be same, but there will be change of sign for the y value. Again the same thing, again the same thing. Um, so this is one example. This is one example. Now I want to change this to other side. So this is my original position. So this is y is equal to 0 line, x is equal to 0 line. So now I want to change that. Now the object is in this position. We assume that the object is here. So now I want to change from this side to this side. So if I want to get the reflection of this object means I have to change this sign. I have to change this sign which is there in the x-axis. So this is x is equal to 0. So on the x is equal to 0, if you want to get the reflected object, if you want to get the reflected object, or if you want to get the reflected position of this original object means you just need to change the sign. So this object is here. Object is on the left side. Object is on the left side of y-axis. So you want to get the reflection of this means the corresponding matrix will be -1, 0, 1 like this. So if you just need whatever value is there, You just need to get the opposite of that. So this can be, the object is on the left hand side, you want to shift it to the right hand side. If you want to get the reflection, means you just need to pass this transformation matrix. If you just pass this transformation matrix, um, you will get this result. Again again you want to get, the matrix in this form. So again, now I want to get the reflected position. So the object is here, the object is in third quadrant. So now you want to move that object to the first quadrant, meaning you want to get the reflection of this object. So for that, both the values will be negative. So when both the values are negative, when both the values are flipped, it will move to this position. See here, then what they are doing means they're just checking with the coordinate signs. The coordinate signs here, it will be negative, negative. So if you apply negative, negative to this, it will become positive, 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 positive will be in first quadrant. So you can obtain, what do we call? So here, this is perpendicular to the xy plane. This is perpendicular to the xy plane, and the reflection for this, the matrix which will represent this reflection is given by this one, this point. So this is the third scenario. So now I want to generate a point. I want to generate a reflection along the line y is equal to x. Y is equal to x means y is equal to x means like 0 0 1 1 2 2 3 3 4 4, like that. So it will come like this only. So if you, this is the original position, this is the original position. You want to get, the reflection for this. So for that, till now it was like 1 1 1 0 0 0 0 0 0. So we were playing with these terms, minus 1 plus 1, like that. Minus 1 means down x, like negative value of x. Minus x means it was coming from left hand side of the y line to right hand side. But now since it is along the line y is equal to x, since it is along the line y is equal to x, since it is along the line y is equal to x, so it will be 0 0. The transformation can be obtained by 0 0, and here replacing with 1 and 1. So again, so this is the original position. You got the reflection for this by using this transform equation, this equation, like this transformation or the reflection matrix. Again, sir, I don't want like this. I want the reflection in this way. How to generate that? So something similar to this. The original image object will be, original object will be here, and I want to get the reflection. So in order to do that, the first thing is you should rotate this object. You should rotate this object by some angle theta, so that the object will come on this x-axis. Now the object will be like this. Now the object will be like this. After that, you should perform, the first thing is rotation. So the object will come from line y is equal to x to y is equal to 0. After that, after that after that, perform the reflection. Once you perform the reflection, it will come to this line. It will look like this. After that, again perform the reverse rotation. Again, since you are rotated by 45-degree, means again rotate it by um, minus 45. So again it will go to this line. So once it goes to this line, the image will come like this. So this is like the rotation along the line, or the reflection along the line y is equal to minus x. So for this also some matrix is there. That matrix is nothing but minus 1, minus 1. See, this is along. So this, I'll just tell the steps for that. You can try that. So this reflection is along the line. This reflection is along the line y is equal to x. So if you want to get the reflection along the line y is equal to minus x, means it will be like this. Along this line y x, you want to get the reflection along the line y is equal to minus x. For that, the matrix is given by minus 1. This is the reflection matrix which will give you this position. So how to do that means, for this line, first rotate such that the line will become y is equal to 0. So rotate this. So this line will come like this. The image will be like this. After that, do the reflection means it will go to the right hand side, it will go to the left hand side, it will be like this. So after that, again rotate this by this much. If you add plus theta means here minus theta, so now the image will go to this line. So these are the steps in which the reflection can be obtained. So rotation, then then again inverse that, not the reflection, just inverse that, and again rotate it back. So in by following the steps you can get the reflection along the line y is equal to minus x. So after this there is one more term called one more transformation called shear transformation. So what it will do means here it will distort the shape of the object. See, here the square is of good size but the shape is distorted. So this kind of transformation will appear as if the object is made up of internal layers which are slided over each other to form shear. So this is the definition. A transformation that will distort the shape of an object such that the transformed shape appears as if the object were composed of internal layers that has been caused to slide over each other. So this is the definition. So how to do the shear means, so this is the matrix, this is the transformation matrix which um, is being given. So here x dash means the shift along the x-axis. So x dash means shift along the x-axis. X dash is equal to this is the equation, and y dash is equal to y. So this is along the x-axis. So if you want to shift the coordinate values along x-axis, this is the matrix. This is the equation. So if you want to shift along the y-axis means you can write it as y dash is equal to. So y dash is equal to y plus sh of y into x, and x dash is equal to x. This is the shear along the y-axis. See, this is the shear along x-axis. See here, I'm changing this with respect to x. Only x value is changing. The y value is remaining constant. See, y value is remaining constant. Y value is remaining constant. X value is changing. So this is the shear along the x values. That is x values. If you want the same thing to be performed along the y things means this is the equation. Y dash is equal to y plus shy into x, and x dash is equal to x, and the transformation matrix is 1 1 1. So 0 shy shy 0 0 0 0 1. You can try this out. So what do you mean by this operation means, see this sharing transformation will shift the coordinate x value. Also here the x direction is related. Here the x direction is being taken into consideration, meaning it is moving in the x axis. So the equation is given, the transformation is given, so you can apply the formula also. So how we are getting this image means, uh, how to calculate x dash means, see, x dash is equal to initial value of x is 0, 0 plus. So if I take some sh shift value to be, if I take the shift value to be 2, if I take the shift value as 2, so 0 plus 2 into 1. So 0 plus 2 into 1, x dash will become 2. So from the initial position of x is equal to 2, the new position is x dash is 2. The y value, y dash will remain same only, y dash will remain same only. So y dash will remain 1 only. Again, for this also, x dash is equal to 1 plus 2 into 1 plus 2 into what was the y dash value? 1. So 1 plus 2 into 1 will be 3. So that's why you're getting 3. Again, y will remain same. But for here, it will be like you're multiplying, y is 0, no? So it will be 0 only. So that's why the on the line y is equal to 0, the equation doesn't change. So this is regarding the shear transformation. So this transformation is also important. So here the shape is getting distorted. The transformation matrix. So here what I'm doing is an x direction shear relative to the x-axis is produced through this matrix. through this matrix, transformation matrix, with the equation of coordinates given by x dash is equal to x plus shx into y plus is equal, and then y dash is equal to y. So this is just a comma. While I was copying that, it has been put up in the slide. So using this formula, if I take the value of this, if I take the value of this as 2, you will get this equation. So the same way, you can also you can generate the x direction shear relative to the reference line given by this formula with reference to the reference line. And this is the transformation matrix. This is a transformation matrix. And also you can get the y direction shear with respect to the reference line x reference by this transformation line and the coordinate value. So these are the other 2D dimensional transformations. So this is also important. We have total 5 transformations. The basic transformations are translation, rotation, scaling, and the other transformations are scaling and sharing. So these are also, see, some packages will support uh, um, only basic thing, and some OpenGL, I mean some graphics, some computer graphics will support these two also, reflection and sharing. So that's why basic. So we have covered the basic 2D transformations and other 2D transformations. So next will be like functions. I think next will be OpenGL functions, which will continue it in the next classes. Those next classes, some OpenGL functions like raster transformation. Then we have learned about translation, rotation, scaling. No, the same thing we'll be studying in terms of the functions, like what is the first term, what is the second term, what is the third term, the syntax that are there in OpenGL. After that, the matrix, how the matrix can be loaded, all those things we'll study. After that, some composite transformations and computation efficiency. So 4 topics are there, I think, which you can complete in the next class. So after that, we'll talk about the 2D pipeline. So you just practice these things. See, here most of the thing is a matrix thing only. So you just practice those things. So you should remember all these equations, all these values. Even if you know the even if you know the basic equation also, you can generate all these things. If you have any doubts, you just let me know. Any doubt regarding today's class? Any doubt? Any doubt? So we have studied about the composite matrices, meaning when multiple transformations are there, instead of doing that individually, multiply them and then apply the result to the initial point. So that is the one line answer. That is a one line answer. The second thing is we studied about reflection. Reflection means one image will be there that will be moving along y-axis, x-axis for 45-degree along the line y is equal to x and y is equal to minus x. And then we studied about shear, which is a distortion. So for that also you can get the distortion of an object along x-axis, you can get an object along y-axis, and for the transformation values. So I'll stop the class now. We'll stop the class now. The remaining we'll sit in next class. So study for the internals. Um, so this